started. We have just a few slides. This won't take very long. I wanted to wrap up the thunderstorm section. And put that to that. And then we will begin the first of two large chunks of material. The first one covers the tropics, and the second one covers the mid latitudes. Okay. And then this is a swing break on your minds. That's good. Be ready. The tropical material, and I updated a couple of the slides. I think you get one of them. I just updated a couple of the graphics in the tropics. We're going to break that up into three. So the first part of the tropics will deal with the large-scale general circulation. Then we'll have a little bit, we might get to that today, not sure. We're going to talk about a very specific tropical circulation very briefly, which is the monsoon. Probably heard of that. And then we'll do a slightly more detailed and not complex, but not tremendously well understood concept, which is El Niño, right? You may have heard of that too as well. So those are the three chunks of the tropical slides. The second set of material that covers the tropics deals specifically with El Niño, and that will certainly come after exam number 2. And then the middle latitudes will go into mid latitude cyclones, a bit more on jet streams and things like that. I think my voice is a bit funky. I'm getting sick and I had a puppy up all night that was throwing up over the bed. So it's been a long night with that little lunch here. Like it's out of town. So, okay. So let's wrap up on thunderstorms. So we've talked about instability and the importance of the vertical structure of the atmosphere in terms of its stability, right? And remember, in dealing with stability, all that does is it gives you an idea whether the atmosphere is conducive to air rising or not, okay? Independent of whether you actually have a trigger mechanism to get air to go up, right? So we want an unstable atmosphere if you want thunderstorms to develop. But it's not an absolute requirement because, again, what we can do is you can bring in a cold front which overrides everything and that'll get air to go up anyway, right? But stability is important nonetheless in terms of rising air. So we've looked at stability, layer stability and parcel stability. And then in terms of thunderstorms, we made some broad general brushstrokes on looking at storms that develop in air masses, so air mass thunderstorms. Okay? As well as sonotically forced thunderstorms that form along cold fronts. So just to wrap this up, there's another way we look at storms, and that is whether storms are single cell storms or multi-cell storms. That's just the wrap up. Hey, we'll be looking at the last bit for the morning. Oh, and just as a heads up, remember we're going to deal with severe storms separately. When we come back after exam 2 and we knock out the mid latitudes, then we're going to look at the stuff that maybe you can wait 12 weeks to get to, right? If there's going to be severe storms, rotation, and ultimately the circumstances under which storms become tornadic or not, so tornadoes. But nonetheless, we can talk about thunderstorms as being single cell storms, which is literally quite that. One cell of air that is rising in some parts of the system and sinking in other parts of the system. And thunderstorms don't just spontaneously appear, right? They have a genesis. And that is what is captured by this diagram here, which is a very simple cartoon of the development of storms. And we generally look at storms, single cell storms, in terms of one of these phases, right? There is the cumulus phase or the developing phase. So this is where you've got rising air. However, whatever that mechanism is, it might be non-frontal convergence, might just be heating, okay? You might have air that's coming up against a mountain, and generally that would be more complicated and be a line or a multi-cell system. But the cumulus stage is the stage of the thunderstorm, the early stage, bless you, the early stage of thunderstorm development that is dominated by updrafts. Okay, so that's the term. Mentioned that a couple of times, but that's specifically the term that relates to rising air within a cumulus cloud. All right, the developing stage, the updraft stage. So buoyancy is key here, and as long as you have generally an unstable atmosphere, then that cloud can develop as that rising air reaches its lifting condensation level and continues to rise. Okay. At some point, those updrafts, presumably there's enough moisture there to grow meaningful cloud droplets, and the processes that we've talked about very briefly, right? The ice crystal process and the collision and coalescence, and eventually you might get raindrops or ice crystals, but predominantly raindrops in warm clouds that will begin to fall through that cloud. And once you get a cloud or a storm that has both updrafts and downdrafts, then you know you're in the mature stage of the storm, right? So the mature stage, both updrafts and downdrafts coexist, okay? And those downdrafts are literally the downward flowing air being dragged through the storm by the falling precipitation. As those downdrafts move out of the storm in front of the storm, you've probably experienced this when the storm comes along. It can get breezy pretty quickly and the temperature can drop. That's a mini cold front. They talk about that as being the gust front of the storm, the leading front of the storm, as those downdrafts rush out through the storm. But the mature stage is characterized by both updrafts and downdrafts. And eventually, those downdrafts will begin to dominate and cut the updrafts off. And then you know you are in the dissipating stage, right? The stage where the thunderstorm is dying out. And the downdrafts are also characterized by sucking in dry air to the storm from the surrounding environment. And eventually the system will die out. So a very simple three-stage model of looking at thunderstorms. Obviously, it develops through time. There's a distinct difference between a single cell storm, and I'm just going to kind of tee this up and then come back and talk about this again when we get back from spring break. When a single cell storm develops into a severe thunderstorm. So let me just tee that up right now, in case you're wondering, can we call a storm like you see in the top right there, where we've got updrafts and downdrafts going on? Can we call that a severe storm? You can't. And here's why. So for a storm to develop into a severe thunderstorm, one of three things have to be happening in that storm. Okay, and I know this is kind of preempting what's gonna come, but I thought I'd get it out of the way now. First of all, if your storm is developing hail that has a diameter of at least an inch, and we will talk more about hail later on because that's the characteristic of severe storms. So if a storm is developing, producing hail that is 1 inch in diameter, or there is a tornado within that storm, a rotating column of air that has touched the ground, or you have winds that are 57.5 miles an hour. And we call those straight line winds. You may have heard that term. A straight line wind is just a horizontal wind coming out from that storm. One of those three things are happening, then your storm can be designated as a severe storm. Okay. And I mentioned that here because, and again, this is just a primer. Yeah.
Oh, is it the gust front that's 57?
Essentially, it's the gust front that's 57, and the winds associated with all of the downdrafts. Yeah, it is. Okay. And the reason why I mention that is that what you see on the screen here, a single cell storm like this, cannot develop into a severe storm, right? And the reason why is that these downdrafts will eventually cut those updrafts off pretty quickly. You shut off the driving mechanism, you shut off the fuel, that warm, moist air that's being sucked into the storm, okay? In a severe storm, this entire thing is tilted over so that the downdrafts cannot cut the updrafts off. Again, we're going to come back and look at that in quite a bit of detail when we get back on spring break. But just in case you're thinking, okay, where does this how does this become a severe storm, or how does this turn into a tornado? The answer is it doesn't, okay? You cannot get a severe thunderstorm until you've got that entire system tilted over. And we're going to talk about why that happens and how it actually happens. Okay, so this is a very simple three-stage model of a storm that would develop predominantly in an air mass system.
What is meant by entrainment?
Okay, good question. So entrainment is just sucking in. Okay, so entraining dry air, meaning it's pulling dry air in from around the storm. Yeah. So that's single cell. And then the other thing, and this will just be kind of the summary slides, is that most storms, unless you're forming thunderstorms literally in a very wide, moist maritime tropical air mass, many storms are what we call multi-cell storms. Okay, so think of it this way: you could get a head of broccoli, right? And you've got a bunch of different florets on that broccoli. That would be a multi-cell cluster of thunderstorms, as opposed to breaking one broccoli piece off and standing there with your one little broccoli head. That would be a single cell storm, right? Most storms are multi-cell clusters because the cells feed off one another. So what you're looking at here is a large storm, okay? And these are individual little cells. There's another cell developing. This is the main thunderstorm here, and then this is a cell that's dying out, all part of one big broccoli cluster, if you like, okay? And as you'll see later on, when we get back from spring break, you'll be able to look at a picture like this and say, well, this is a severe thunderstorm, and there's 2 or 3 things that are going on in that photograph that will tell you it's a severe storm, but you'll get that. So in a sense, this is what the majority of storms really are. Is multi-cell clusters, where you've got warm air being entrained from the back, more rising moist air. So this is the cumulus developing. This might be the mature phase right here, and then eventually the downdrafts cut that storm off. And very often, the gust fronts here become the feeding mechanism for future cells, right? So this might be stage 1, okay? And this is the mature cell here, and this is dying out at the back. And this warm air rising up the gust front then becomes the next part of cell number 5. And cell 4 begins to develop. That will then become a mature storm and eventually die out. They become self-feeding, if you like, in these multi-cell storms. Anyway, that's the rule rather than the exception. I think there's one more picture here that shows the same thing. Yeah.
Which of those is the cloud condensation level, the bottom or the top where it's kind of starting to cut off?
Say again?
Like, is that the right term, the cloud condensation level? Or where's the 850?
The looking condensation level? So the looking condensation level is right here, right? So that's the base of the cloud. Here's your LCL, okay? That's an interesting question. I'm glad you raised it, because you look at, so you will always take this to be the lifting condensation level for sure. And then just looking at a storm like this, if you think back to what we've covered with the thermodiagram, right? Your question would be, well, where's the level of free convection? You can't determine that visually, but somewhere here is the level of free convection. Remember, the mandatory levels are 1,000 millibars, 850-ish, which would be the LCL. Clearly, that's an average, right? 700 would be right in here. That's about the 3-kilometer level. Okay. At this point, you're certainly above the limit of free convection if you're looking at a storm like this. Right? The top of the clouds here, this would be the limit of convection, LOC.
Question is, what cuts off the storm if the gust front's feeding in?
So the gust front, that's a good question. So the gust front is coming out in front of the storm, pushing into that warm, moist air, giving it a bit more of a bigger mechanism up in front of that, right? But the downdrafts are being cut off by, the updrafts are being cut off by the downdrafts. They begin to dominate as most of that rainfall begins to fall through the cloud.
So like the gust front would cut off the hot or the moist warm air, like if there's enough of it.
If there's enough of it, yeah. But generally the gust front acts as a nice little trigger mechanism, a mini cold front, for allowing that warm, moist air to continue to rise up. Yeah. Yeah. So that's a simple look at thunderstorms, single cell, multi-cell, and then again, we can come back and really pick apart how these storms, the conditions under which these storms develop into severe systems. All right. Let's start this big section here. Let me rub this out. Okay, so we're going to look at the tropics. And I've labeled this tropical 1 the general circulation. So let's get started with this. So this diagram here is a composite satellite image, meaning it's a mosaic. It's a snapshot of all the satellites around the planet. Okay, and I've drawn in the blue lines here. So here's the equator right there, 10, 20, 25. The blue rectangle is essentially 23.5 degrees north and south, and the red is 30 degrees north and south. Okay. So when we talk about the tropical circulation, technically, strictly speaking, it's 23.5 degrees north and south, right? Because the Earth is tilted at 23, but we also then nudge it a bit further. A lot of people talk about 30 degrees to 35 being the subtropics. There's no hard and fast rule. When we talk about tropical meteorology, I just like to wrap it all around 30 degrees north and south, right? In that band. Infrared or visible? How they made this composite image? Infrared satellites or visible? Infrared, yeah, right. You can see our old friend, lots of gray. Okay. What do you notice about the satellite image, the snapshot? Let me just take a look. This is an old one. This is 2002. This is 8th of October, 2002. What are some of the things you notice about this?
All of the cloud coverage tends to lie above the 30 and below the 30.
Okay. Keep going. A bit more, Ryan? What else do you see?
I was gonna say the same thing, but it kind of looks like they're like it's I don't know, is it circling? I don't know, it's like rotation.
This is a really, I love this one because it captures so much of what's going on, not just in the tropics, but the middle latitudes as well. Let's focus in the tropics for a moment. Focus in the red or blue.
High cold cloud.
Yeah, a lot of high cold clouds, right? Infrared image, bright white on an infrared image is high cold. Okay. Lots more gray in the middle latitudes. Good. Why?
Energy distribution.
Yeah. What about the energy distribution? High cold clouds means? Yeah. All you got to remember is that tall column of warm air, short columns of cold air, right? You've got those towering, rising, towering columns of air going up to the high levels of the troposphere. What else do you notice about the troposphere?
That's where all the storms storm
Where?
on the
Like-
equator.
Okay.
Like in the Gulf of New Mexico, it feels like something starting to rotate.
Something there. Okay. What else do you notice? There's one really important feature that there's two important features in the tropics that we're gonna pull apart here this morning. It's what?
Mostly over the ocean.
What?
The cloud coverage and this one.
Okay. Yeah, so you go to the oceans. There's cloud cover, it looks like a band, it gets really messy here. It's something here. What's here? The rainforest, good. This is the Amazon rainforest, right? So there's lots of cloud here, a lot of evapotranspiration and moisture with the rainforest. Okay. It's a bit messy here. There's a band here. It gets very messy through here. We're going to talk about that. Right? Would you agree that it looks like there's more or less a band, sort of cloud in and around about the equator? This is October, so the subsolar point is just beginning to shift into the southern hemisphere here. Again, this is the equator over here. Right, so the subsolar point would be 21st of September, so the sun is probably directly overhead about here-ish. Okay. And then the middle latitudes are messy, right? We're gonna come back and really look at what's going on in these regions here and being a focus in here. What's the other thing that jumps out at you in the tropics here, do you think? No, well, no, not this image, but we're gonna come back and talk about El Nino and La Nina and how that impacts global weather. So as opposed to all this cool cloud, what else do you notice? What?
Water.
Yes.
There's no one cloud?
Yeah, right. There's lots of areas here where that are cloud free, big splodges of cloud free area, right? Which is another very distinguishing characteristic of the tropics. The meteorology of the tropics is actually quite straightforward, okay, which is the good news for you. Pretty straightforward, because remember, the tropics are always in an energy surplus, right? And the poles are always in an energy deficit. Remember, we said the reason why the tropics don't heat up or overheat, they do heat up and they don't overheat, is that they get rid of all that energy surplus by sending out warm winds and warm ocean currents and things like this, right? Big disturbances, like a hurricane, that's actually just dying out in that particular image there, okay? But the meteorology of the tropics is relatively straightforward because it's all driven by the thermodynamics, the fact that the tropics have this excess heat energy and they're trying to get rid of it, okay? The other thing just to mention off this slide as we get going is that this band here between 30 degrees north and 30 degrees south, right, represents exactly 50% of the surface of the planet. Okay, so the tropics are big, right? When you plot this on a Mercator projection, your typical projection that you'll see, the tropics only look like they cover a third, right? And that you've got 30 to 60 and 60 to 90, but remember the Earth, I think, is round, right? And so the bulge in the middle means that the tropics actually constitute half of the planet's surface. So they're super important. So don't think that we're only dealing with a third of the atmosphere. We're not. We're dealing with half of it, okay? And what that actually means.
What's that swirling air mass on the right,
Where?
on the far right?
This one here?
Yeah.
Yeah, that's another tropical system. That's a typhoon. Yeah. The typhoons, hurricanes, and tropical cyclones are all exactly the same system. We'll get to that. It's just where they form. Is what's going on. All good so far. Okay, cool. All right, I'll go back 1 second. So here are the Galapagos Islands, and let's go to this point right over here. Okay. And this next diagram in the slides is taken from that particular point. It shows the wind field from I still can't get used to pronouncing it like this. In South Africa, we call them buoys. You call them buoys? Yeah, I can't do it. So this is from an oceanic buoy, okay, that has some instruments sitting on the top of it, and it's measuring the frequency of occurrence of wind, okay? So it's measuring the wind speeds and how often those wind speeds occur. So every hour, what the average is. And then it's plotting the frequency of occurrence of the wind direction. So every hour, the buoy takes a measurement and goes, okay, the average wind speed is this, and the average wind direction is this. And it does it every hour for 365. Okay, and it plots it in what is known as a windrose diagram that shows the frequency of occurrence and the direction. So this is 10%, 20%, 30%, 40%, and the direction of the winds from this little bobbing thing in the ocean. What do you notice about the right-hand diagram? The direction of the winds at 8 degrees south of the equator. Brian, if you were designing the golf course here and you wanted to play every shot downwind, you would orient every single golf hole in that direction, right? The wind here is all coming out of the southeast. Almost 45% of the winds, almost half of all of the winds are coming out of that one direction, okay? the southeast, and a little bit of variation on the sides. Okay, east, southeast, and south. It's a southeast wind, morning, noon, and night. That make sense? And if that buoy was dragged across the equator and went to 8 degrees north, this would do that. And it would just be northeast. Okay, and that's one of the key features of the surface winds in the tropics is their consistency of wind speed and wind direction. Okay, so in the southern hemisphere, in the tropics, those winds are coming out of the southeast. And in the northern hemisphere, they're coming out of the northeast almost all the time, with little bits of variation, right? And these are the trade winds. Okay, the southeasterly trade winds and the northeasterly trade winds that are so predictable and so consistent, and that's why they're called the trade winds. Is that before we had airplanes, people trying to go around the, get from Europe to Asia or get around Africa to get the spice routes going, or coming across to the New World, across to the United States. You wanted to get into the trade winds because you knew that they were predictable and consistent. Okay, there's Hawaii, for example. So the trade winds are, I suppose, the distinguishing characteristic of tropical circulation. And they meet along this. We're going to talk a little bit about this morning. The Intertropical Convergence Zone, the ITCZ, right? So the ITCZ is this region where the southeasterly trades meet the northeasterly trades.
Is that the equator?
I'm glad you asked that. It's not at the equator, but it's in the equatorial region. Okay.
Does it change based on the?
Yeah. The ITCZ migrates. Okay. If the Earth wasn't tilted, and if there wasn't any difference between land and water, let's just say the tropics were completely covered with land surface and the Earth wasn't tilted, then the ITCZ would lie right at the equator, and it would sit there morning, noon, and night, every day, 365 days a year. If the Earth was upright, and we didn't have any influence of land or water doing it. Okay? But we know, of course, from one of our very early lectures, that the subsolar point migrates. Right? It goes to 23.5 degrees north and it goes to 23.5 degrees south. And as that subsolar point migrates, because of the seasons driven by the axial tilt, the intertropical convergence zone migrates with that subsolar point. But it's complicated and it's messy, and you'll see why in just a second, because of the darn land ocean differences. Okay, so we've got trade winds. And I'll show you just a couple of images there, and then we'll start picking apart exactly how these trade winds form. So this is an image from the book. It shows average annual rainfall in millimeters per day, right? So this is 10, 15, 20 millimeters per day. 25 millimeters is an inch, okay, per day. And this is in August, right? So this is August, so the subsolar point is, well, it's probably pretty much where these ribbons are. Okay, so you see this band, this is the intertropical convergence zone. It gets broken up and gets messy over the Amazon, right? Because of all the evapotranspiration going on there and a certain circulation pattern here. It picks up again over here, and then it gets broken up a little bit here as it moves over the great African forests, right? So the intertropical convergence zone, the rainfall rate over the open ocean surfaces is pretty straightforward. Okay, you've got evaporation of the ocean surfaces and rainfall pretty much there. When you get over the land surfaces, it gets a bit messy and it gets very disturbed. It's just off the map here. It gets disturbed when you get over the Indian subcontinent because of the monsoon, and that's something we're going to come back and talk about as well. It's all linked to how this thing migrates, right? So for now, the intertropical convergence zone is this sort of semi-continuous band of convection wrapping around the tropical regions. Okay. So how does this all work? Why do we get these trade winds and these areas of clear air? So this was the first meteorologic diagram that I'm aware of. And this was drawn in 1735 by a scientist called George Hadley, Hadley. You can see his name in the bottom. And he put forward, so he was trying to explain why the trade winds are so consistent and persistent. persistent. And so he came up with this model. So this is looking at the side of the planet, and here's the equator here. And he said because the tropics are always warm and moist, okay, you've got this rising warm air over the tropics. And he said it moves out towards the poles and it sinks in the polar region and then comes back towards the tropics, right? Hadley posed that in each hemisphere you had these single big gigantic cells that were overturning like this. So if this is the equator here, these cells were simply doing this, moving the warm air out towards the pole, cooling and sinking and coming back towards the equator, right? He got part of it right. The part he got right is the part that relates to the tropical regions. Because the returning limb of this cell coming back from the polar region here, remember in the northern hemisphere, it's getting deflected, so I'm going to stand here. That polar cell is coming back towards the equator and it's getting deflected to what direction? To the right of its path by Coriolis, right? Okay, same here. In the southern hemisphere, the wind is being deflected to the left of its path. Okay. So as these returning limbs here of these cells that Hadley put forward, they get deflected to the left, and that Hadley said explained the southeasterly and the northeasterly trades. And he was spot on. That's exactly what happened. What's not right is that these cells extend from the tropics all the way to the poles. Okay, they stop short here at about 30 degrees north and south, and we'll explain why in just a little bit. Okay. So that was the first look at an explanation for the consistency and the persistence of the southeast and the northeasterly trades. Hadley was saying it's just simply the returning air coming back from the poles, getting deflected to the right and to the left of its path because of the Coriolis effect. All good? Okay. Here's what actually happens. And this again is a bit of an oversimplification, but it works pretty well. So we're looking here at the equator, subtropics on the left, subtropics on the right. This is right at about 30 degrees, right? About 20 degrees, 10 degrees in India. So when you look at a slice through the atmosphere here, through the atmosphere from the subtropics to the equator, this is actually what goes on, right? You've got all of this warm, powering columns of air, all of the energy surplus. That air then begins to move out. It rises up. The dash line here is an indication of the upper pores, the top level of the atmosphere. So that warm air rises and it begins to move out towards the polar regions, right? And as it begins to move out towards the polar regions, what happens to it? It starts getting deflected to the right of its path in the northern hemisphere, right? And it begins to not only get deflected to the right, but it's cooling and begins to sink back down. And that happens at about 30 degrees north and south. Okay, Hadley didn't get that right. We don't get these thermally direct cells going all the way to the poles. Okay, so the air begins to move out from the tropics here, and it then begins to sink at about 30 degrees north and south. And as it begins to sink down towards the surface, part of that sinking air returns back towards the tropics, and part of it moves up towards the middle latitudes. The left-hand side of the diagrams here, we're going to come back and talk about after spring break, right? Let's just focus on these. So what you see here in this diagram, these big cells that Hadley drew extending from the tropics to the poles, is just simply this part of the cell that stops at 30 degrees north and south. That make sense? I'll come back in just a minute and talk about exactly why that air begins to pile up at 30 degrees north and south.
So it goes back toward the tropic to the trade winds.
Yeah, it goes back.
Where else? It just goes back to the poles.
Yeah, so it goes back towards the tropics here, and then it begins to move towards the poles where it then meets polar air along the polar front, and we'll come, that's part of the middle latitude story. Okay. Okay.
How much of the air that's going out goes to the poles?
Oh, I've never seen a percentage. It's a wild guess. We were looking up. I'm gonna guess about 20 to 25%, something in there. Most of it comes back to the problem. Yeah. And then as it moves back towards the tropics, remember, what's the air doing here as it's sinking? It's temperature wise, what's it doing? As it's sinking, it's
Well,
In training.
children, rising air, sinking air. There you go. Okay, so as the air is sinking, it's warming by compression. If it's warming, it's doing what relative to its dew point? It's getting closer or getting further apart. Getting further apart. Yeah, it's going to the right of the saturation vapor pressure. So as this air is slowly sinking, it's warming. And therefore, you think it's getting cloudy and rainy, or you think it's getting nice and clear? Nice and clear. That explains the big clear splotches across the satellite image at about 30 degrees around the planet. Okay, it's not absolutely perfect because land masses and mountains and sea breezes and other things mess it up a little bit, right? But generally speaking, that's why you have these big high pressure zones around 30 degrees north and south. It's because of the sinking air on this limb of the Hadley cell. And incidentally, we call this cell in each hemisphere the Hadley cell, after the great man himself, right? So the Hadley cell in each hemisphere is what we call, I'll put this term up here because it's reasonably important. It's what we call a thermally direct cell. In other words, it's driven because of the temperature contrasts, right? Because of the energy circles. It's a thermally direct cell. Oops. So in each hemisphere, we have a Hadley cell, and as that air begins to move back towards the tropics, okay, now in this area it's dry, right? This is higher pressure. And as it's dry, it starts moving across ocean surfaces and it starts picking up moisture. So we start increasing the cloud and increasing the cloud and increasing the cloud until you get to the intertropical convergence zone and you're off to the races again. That's where the greatest heating. So in each hemisphere, you've got these Hadley cells doing this. If I'm standing on the equator, they are thermally direct. Okay? Rising columns of air along the ITCZ, sinking, warming by compression, higher pressures over there, rising air. And so along the equatorial region, underneath the intertropical convergence zone, is generally lower pressures. And I'll show you those maps in just a second. Right.
So when you say like it's slowly rising when it comes back towards the equator and then the equator rapidly rises?
Correct.
Or it's just constant?
No, that's a good way to phrase, right? So the equatorial regions, I don't know, 10 degrees either side of the equator, that's the most unstable because that's where the heating is greatest. That's where the energy surplus is greatest. All good? It's a really simple model and it works super well in terms of explaining the high pressures, the low pressures, and also this, remember, is the trade winds. It's just getting deflected to the right and coming out of the northeast and getting deflected to the left in the southern hemisphere and coming out of the south, right? So these thermally direct cells, and they are there for one reason only, and that's to get that excess heat and moisture out of the tropics towards the poles. Okay, cool, all right. Okay, so let's introduce a little complexity here, and that's this seasonal shift. So this shows average sea level pressure in January and average sea level pressure in July. The hotter the color here, so the oranges and the reds indicate high pressure, and the cold colors indicate low pressure. Okay, and the black dashed line here is the line of lowest pressure, which is we call it the equatorial trough. It's basically the ITCZ, right? So just look at this for a second, let that sink in. So this is January. Where's the subsolar point in January? Subsolar point is 23.5 degrees south, right? So the sun is directly over here. That's 10, 20. The sun is directly over here, overhead here, right? And if latitude was the only control, and there was no land water differences, then where would the equatorial trough be? It would be one horizontal fat dashed line doing that, right? But it's not, because we've got the land water differences, and mountains also mess things up a little bit. Okay. So the ITCZ, the equatorial trough, this region of lower pressure, you can see shows up anchored here in January, right? Right over the Great Australian Deserts. Why? Because they're heating up super rapidly. Okay. So that anchors that trough here. Look at July, and so look at the high pressures here. You see these big blobs of high pressure. Okay. And then you look at July, so where's the subsolar point here? The subsolar point is right here at 23.5 degrees north. Okay. But this equatorial trough, or the ITCZ, when you get out over the Pacific, right, this gigantic ocean, then it begins, it's anchored here over the land that's heating up, and then it begins to dive back down towards the equator. So it's complicated because of the land water difference in terms of where that direct heating goes. The equatorial trough is also known as the doldrums. Okay. It's not that they're depressed. You probably heard that come feeling a bit in the doldrums. They're feeling a bit down, right? It's the winds are really light. Okay, super light winds because it's sitting in the trough. Remember, you're sitting underneath the rising columns of air in the ITCZ. It doesn't mean to say that there's no rainfall. You get lots of rainfall. It's just that you don't get lots of wind, okay, in the doldrums along the equatorial trough. Very weak surface winds over there. A couple of other images. Here's another one showing the ITCZ. So this is August 2003, right? So here's all of the convection over here. Again, it gets pretty messy over the Amazon, comes down through, it gets pretty messy over the rainforest here. We're going to come back and talk about the monsoon that doesn't mess it up, right?
Oscar, that just goes to show that the ITCZ moves over the seasons.
Yeah, I'm going to show you another couple specifically showing the ITs. Yeah. Yeah, so it's just showing this whole thing is shifting. Remember, it's shifting like this into the northern hemisphere and southern hemisphere. But instead of just doing that, it's kind of like doing this Mexican way, where it's doing that. It's saying, okay, where is the land heating up more quickly? That's where I will anchor myself, and the rest of you can catch up later, if you like. Okay. Okay, so there's another one. Who in the room here is going to South Africa in July? 1, 2, 3, 4. Okay. Anybody else flown from Europe to Africa, to Southern Africa before? Okay. If you've either done it, or if you're about to do it in July, you guys will be coming from New York and you'll come through here. Now, if you're good people, you'll be asleep, but you may get woken up. I know every time I fly from Europe back home to Cape Town, without fail, you'll hit turbulence when you get through the ITCZ, right? On your way. You'll feel it for sure. Unless for some reason it's very, very weak at that particular moment in time. But without fail, coming down through Central Africa, we always feel the ITCZ going through those towering columns there. For sure. Okay, so this shows it more specifically. Okay, so here's, and it shows it not just in terms of pressure, but now we're looking at temperature. So here's the January situation. Again, you can see how meandering the ITCZ is, and it's anchored right over the Australian deserts. Okay, that's where things are hottest. So that's July. Sorry, that's January, and this is the July situation. Right, the July situation is it's anchored here over the Sahara, comes up here over the deserts of Saudi Arabia and Pakistan. This becomes really important. Okay, this big bulge in the ITCZ, that governs the monsoonal circulation that we're going to talk about. And then it meanders across the Pacific, essentially just mimicking the lines of latitude. If the entire planet was covered with ocean water, the ITCZ would look like that. It would simply mimic the lines of latitude. Make sense? Okay. Cool. So this is the summary diagram then, and then I'll show you the summary picture of the general circulation. So this is global pressures on average. Again, red is higher pressure, blue is lower pressure, average sea level pressure is 1013, okay? And you can see these big blobs of high pressure. If we didn't have land masses and mountains, what would this look like? This would be one solid high pressure here, right?
Why is average sea level pressure that when most of it is?
Say again?
Why is average sea level pressure 101.3 when most of that is in that?
So, yeah, so it's misleading, right? Because it's the way in which it's projected. Remember, this is 50% of the surface of the earth. Okay, so that's 50%, and this is an enormous region of lower than average sea level pressure, right? The equatorial trough. And then you've got these troughs over here, and that's along the polar front. That's something different. Okay. The way in which things are mapped, putting a globe on a flat map is always tricky, right? But it all averages out. It truly does. Okay, so the question is, what does the actual general circulation look like? This is an older diagram. I always use this one. I don't know. I've just gotten used to it and I like it. But so here's the equator. Here's the ITCZ over here in the doldrums, and this shows the Hadley cell. Okay, so there's the Hadley cell sinking, and this is the southeast trades and the northeast trades. So this is the Hadley cell in each hemisphere. The diagram on the left, I think, to me, always helps explain why we get the high pressures at 30 degrees north and south. So we're looking down on the North Pole here, and that's the equator, and then this is 30 degrees north. So what this is doing is looking down on the planet, and the air is rising vertically here, and then it's moving towards the North Pole and getting deflected to the right in the northern hemisphere. And all of this deflection to the right, the air literally begins to pile up at around about 30 degrees north. That's where you go from the 8-lane highway down to a 2-lane highway, right? If the Earth was rotating more quickly, what would that look like? If the Earth was rotating more quickly, where would those high pressures be, do you think? Do you think they'd be further north or further south? If the Earth suddenly started speeding up? Why? Yes. Yes, exactly, because your Coriolis force would be greater, right? So if the Earth started speeding up, the winds would get deflected more quickly to the right, and they'd start piling up probably at about 25 or 20 degrees. Conversely, if the Earth began to slow down, right, the rising columns of air would move out towards the poles, and they would get deflected more slowly, and those high pressures might be at 40 degrees, something like that. Does that make sense to everybody, right? So the rotation, the Coriolis effect, and this axial tilt, explains probably 80% of everything that we need to in this class. And that's why we get this piling up of air at 30 degrees. And as that air begins to pile up, so it does this, it rises at the equator, gets deflected to the right, it's cooling, and it begins to sink down like this on top of me. And part of it does that and goes back, and part of it goes to the polar regions. When we look at the general circulation, I'm just going to point out a couple of other features, and then we'll leave that and come back to that after spring break. These two cells are thermally direct, right? The Hadley cells, they're there because of the energy surplus. We've also got big blobs of cold air over the South Pole and the North Pole, right? It's literally taking a balloon filled with water, just dropping it on the North Pole. You've got this big blob of cold air, the energy deficit. Those are polar cells. Okay, they're also thermally direct, but they're not flowing because of the heating. They're flowing because of the cooling. They're cold and chilly, right? So we've got Hadley cells and polar cells, and then we've got these cells here in the middle latitude that we're going to come back and talk about later. They're weak. They're not thermally direct, because in the middle latitudes we've got westwards, and that's a whole nother animal. Okay, I'm going to leave that for a second. These high pressure systems that occur at about 30 degrees north and south, right? You can see them. This is one over here, right? There's one over here. There's a nice big one over here. again, so the green here is rainfall rate, so this is average annual precipitation in millimeters per day, right? So this is obviously the ITCZ, rainforest, evapotranspiration, all sorts of combination. There's the ITCZ, Amazon rainforest, and so on. So these high pressure systems characterized by sinking warming air are clear skies, and there's no coincidence. And when you look at the high pressure system and where the great deserts occur, there's a very strong correlation, right? The major deserts of the world occur under these high pressure systems. There's some caveats here, right? Let me just go back for a second. So here's a high pressure system that sits here. Okay, and then what do we have going on here? Well, we've got the Andes, which messes things up, right? So mountains mess things up. We've got the Atacama Desert here, which is there and only there because of the sinking air. But the mountains on the other side mess things up a little bit. But the Sahara, the Great Deserts of Arabia, the Simpson Desert in Australia, those are all there because of the sinking air under the high pressure systems, right? The compressional warming of the air. All good. So far, okay. Oh, good. I think we have time to just do the monsoon. Let's do the monsoon. This won't take very long. And then I'm going to give you a break. My third slide. Give out. We'll talk about El Nino when we get back from spring break, because El Nino is very important and a little complicated. So the monsoon, you've heard of the monsoon, right? What comes to mind when you hear monsoon? You think?
Cycling.
Yeah, cyclones, big time rainfall, right? So the monsoon is generally associated with the Indian subcontinent, okay? And it's a period of extraordinary rainfall across Pakistan, India, Bangladesh at a certain time of the year. So this shows the average July surface temperature, and here's the ITCZ. You saw this a little earlier, right? And because the ITCZ here and the thermal ridge, the area of highest pressure, highest temperature, okay, follows up through the Arabian deserts, through Pakistan and wraps around here. There's something here going on, right? That's the Himalayas, which blocks everything, okay? So this low pressure, very warm air bends up around the Indian subcontinent and comes down like that. That allows massive amounts of moisture to flow off the Indian Ocean here, north into the Indian subcontinent.
If the Himalayas weren't there, would that then be higher?
Yeah, good question. If we ironed everything out, it would probably do that. And then who knows what could go on here.
Would that be due to like a tectonic region, like the tectonic?
The Himalayas?
Well, the monsoon in general, because of the elevation. Like it's happening.
So, yeah, not quite sure what you're asking in terms of the tectonics.
Like, because mountains help this because they're steady going up.
Right, so the mountains are there,
Right.
okay? And you'll see in a second how the mountains exacerbate, they increase the rainfall dramatically. So the mountains are playing a role for sure,
Right.
okay? But because they're so high, this ITCZ cannot migrate to the northern side of the mountain. Can't do it. So that's what the ITCZ looks like, okay, in July. Yeah, right.
So is this the? Are you saying the ITCZ is like? It produces a lot of precipitation, or is it the Himalayas that produce a lot?
It's both.
Or
No, it's a combination. You'll see that in just 1 second. Yeah, it's a combination, right? Because the rainiest places in the world are along the foothills of the Himalayas here. Throw in a couple of places on in Hawaii as well, okay, on Kauai, for exactly the same mechanism. So what this does is that the fact, remember this ITCZ is the area of highest temperature, but also it's the lowest pressure. It's the equatorial trough, right? It's that trough of low pressure. So it's bending up here. Let's see if it shows up in the next one. So this shows average surface air temperature in May, right? In degrees Celsius, average. You see it comes across here, it's anchored up here, UAE, Saudi Arabia, and it comes across the Great Deserts in the northern areas of India over here in Pakistan. You can just see how quickly those temperatures change along the Himalayas to the right. But this is the important one here. It comes on out. Okay, so this shows, I'll just go back a second. So here is the Arabian deserts in India. So that's temperature. And then this shows the pressure, right? The pressure patterns. And that equatorial trough, the ITCZ, that's doing this and wraps around like that, causes massive amounts of moisture to flow in May, June, July, August off the Indian Ocean, right? If the ITCZ was suppressed and it was down here and shifted down south, then there would be no monsoon. So the monsoon technically is this dramatic seasonal shift in precipitation, right? That occurs over the Indian subcontinent because all of this moisture can then move from the Indian Ocean onto the Indian subcontinent. And so when you look at, so it's basically, this is not technically correct, but it's a good way to think of it. It's a gigantic sea breeze. Remember the sea breeze, and we looked at that with Florida, right? The land heats up more quickly. And if the land heats up more quickly here, you've got relatively lower pressure, and the air then moves onshore. We looked at that with Florida. This is just on a vastly different scale. So when you look at rainfall, for example, so here's the Himalayas here, and there's a town here called Cherrapunji, which is up in the mid foothills of the Himalayas. That's the annual rainfall, broken down by month. We've got inches on the right and centimeters on the left. Okay, just look at the scale here. Fort Worth, how much rainfall do we get in Fort Worth in a year? You know, about 35, 36, 37ish, somewhere in there. Okay. So this is rainfall in Cherrapunji in June, about 120 inches in 1 month. Okay, so that's 4 times our annual rainfall in Fort Worth occurring in just 1 month. It's about 400 inches of rainfall. So huge amounts of moisture coming off the Indian Ocean, and all of that moisture then comes in like this, and what happens? It hits the Himalayas. And so it starts rising very rapidly, orographic force, right? It gets to its saturation vapor curve almost immediately. So you've got essentially an unlimited amount of moisture, and you've got the world's tallest trigger mechanism sitting right here. That brings in vast amounts of rainfall. And then you can see once the ITCZ then begins to shift south and does this and goes into the southern hemisphere, and you get a high pressure system sitting here in December, January, February, your rainfall dies out to almost nothing.
Why isn't India then more lush with like vegetation if they get that much rainfall?
Well, I mean, it is, but it's almost all agriculture. Yeah. Have you ever been? Cool place, fascinating place. But you look at India with 1.4 billion people, I mean, it's just essentially all agriculture. It should be lusher, but it isn't, because it's all farmland essentially. So that's the monsoon. We do get a monsoon here in the US, but it's nowhere near on the same scale. I don't know if any of you have heard of it. Out in the desert Southwest, we get summertime heating, and you can get some intense thunderstorms, and people say, oh, it's the summer monsoon happening in Arizona, but it's nowhere near that. It's not even really a monsoon technically. So that's one tropical circulation that's super important, and it's driven by the location of the United States. Okay. The next thing on the list is this, okay, and we're not going to get there today because we've got to talk about El Nino and southern oscillations. I'm going to give you nothing early spring break. Question, anybody? Okay, so we are back on the 25th. And just looking at the schedule here, we'll do El Nino, see where we are, then we'll do a review and nothing coming down. Cool. Okay.
There was a hypothesis like this, I don't know, swap it, like if the earth is set up that the air deflected further south.
Yeah.
like, I just kind of got lost.
Yeah. So So what is the other, once again, 2030, right? And the earth is rotating, so the earth is rising and it begins to move. And if you reflect to the right and moving path, right? But if one gets reflected to the right, it's path, all of this is tiling up here with about 30 degrees. Okay? If it starts spinning more quickly, then the deflection is going to be faster. If it's Coriolis effect, if the deflection is going by the rotation. If you speed up the rotation, things start getting deflected more quickly. So if you and I are on a merry-go-round, we're going very slowly and we're tossing a ball, we're probably okay. If you start speeding that up, that's the ball at you, you're over there and the ball's over there. For you, it looks like it's going like that, right? Does that make sense?
Yeah.
So the deflection happens more quickly. So a faster spinning earth would mean the high pressures would be further towards the equator, and the slower spinning earth would mean the high pressures would be more towards it. But just
Okay.
shift everything. Does that make sense?
Yeah, I think I got it.
Sweet.
It's gonna be like a dumb question, but back on the Hubble cells.
Yeah.
The polar cells, is there like a polar tornado
No,
if it's spinning?
oh wait, oh, well,
Like in the polar cell, if it's spinning,
there is a vortex, it's not a tornado.
Or like-
Yeah, so it's called a polar vortex,
oh,
circumpolar vortex.
and so there's one on both poles.
Yeah, there is, and it's stronger in the southern hemisphere. Why?
Because there's
Much stronger.
more. I mean, there's less than that.
Southern hemisphere over the Antarctica,
I don't know.
polar vortex. is-
More like that.
Yeah, more land, much stronger. Yeah, there's a big country covered with ice. Yep.
Thank you.
So, I normally do, but I'm gonna have to, let me just see what I'm gonna have to probably. Okay, I'm gonna have to get home. Yeah, I'm gonna have to shoot home. I've got a sick dog and my wife's only gonna get home by 1:30, so I better go check on the house. Is that okay?
Yeah.
Can we get together?
We can just wait till after spring break.
Okay.
You said the exams on the first,
Yeah.
right? Okay, I got time.
Okay.
Your puppy starts feeling better.
Oh, man, poor thing.
More question.
Okay, what's up?
You just have to look at the height and look at the numbers, that seems somewhat.
Yep.
Okay. And then, when you say the amount of liquid being carried,
Hmm.
is that the absolute humidity?
The amount of liquid that's the total
Being
amount of
carried
liquid.
more?
Yeah,
Basically, what is,
so that is,
that the relative humidity or the absolute?
that's the absolute. What's that, what's the question?
This one's just say starting at LCL, lifted up to here.
Right,
I haven't looked at some. I think it might be that.
yep,
So,
yep, it's 40 kilopascals.
that's it. But, I did some, let's see.
Yeah.
I have the note here. So like, would it be like? This minus this, sorry,
So,
Yes,
yeah,
this
so what
minus
was the
this.
mixing ratio you started at here? I can't remember. 17, did you
It's
say?
17.
Yeah.
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 At the dew point.
Right, so
And,
that's the total amount of moisture that's carried all the way up, no matter how high it goes. The question is, how far does it deviate between the liquid and the vapor?
Oh, so you started 17.
Yeah,
Okay, so
Yeah.
it'd be like, is it 17 minus this number?
yeah.
Okay, so this number doesn't matter.
Nope.
Okay.
Yep.
Alright. And then. Is this different than like? The like mixing ratio, or is that just?
It's just another way of phrasing it.
Okay.
Total water is, that's the 17. That's the total amount of water.
Okay, so. The saturation mixing ratio doesn't, we're just taking it down.
Yeah.
We're just taking it down, doesn't really matter.
Yeah.
Okay, and then. Oh, yeah. Is the LOC just the top point of the
Mhm.
cape? Okay. That's
The limit of convection. Geez, man, you're almost done before spring break.
Well, I just had to do it because I was gonna forget.